Welcome to the fifth lecture of the course Mathematical Finance. And this week we are going to be talking about the valuation of path-dependent and American-style options, and we will be covering chapters 9, 10, and 12 from the book by Yoshi. So up to now, we have considered basically European style options where you say, I have a single time slice, capital T. That's typically the maturity date of the contract. And then I have a payoff function that is a function of one of the underlying variables or the underlying variable, for example, the stock price that you observe at the maturity date at time capital T. And this payoff is then a predetermined function f of st. For example, if this is a call option, it's the max of st minus k and 0. And if it's a put option, it's k minus s capital T, comma 0. And what we're going to do now is do kind of a natural extension where we will consider a larger class of so-called multi-look payoffs, where we say we are at the end date or at the maturity date capital T, and then we basically look back along the path we have followed to arrive at time capital T, and then our payoff is a function of multiple values of the stock price that we have observed at time T1, T2, ... until time Tn. And examples of such multi-look payoffs are Asian options, where you take the average of the observations along the path that you have followed. We have discrete barrier options, and we also have things called look-back options, where you basically look back along the path and then say, what was the maximum value or the minimum value that I have taken along each path? So some examples of traded contracts in the real world is a class known as Asian options, or also known as average rate options, where I compute first the average of the stock prices or of interest rates or whatever variable. I compute the average of some variables along the way, and this average is the summation for j is 1 to n of the stj, and then I multiply this with 1 over n. And then I can do a call option type of payoff where I say I take the maximum of the average value minus k and 0. Or you can, this is known as a fixed strike Asian option. And you can have floating strike Asian options where you say I compare the last value stn or s capital T against the average of the observations that came before between time j is 1, T1 until Tn. And obviously we can do k minus the average, which is then like a fixed strike Asian put option. I can take the average minus the final observation, and then we have a floating strike Asian put option. And you can also work with weighted averages where you say I'm not giving all the weights an equal weight 1 over n, but I could use non-equal weights where with some fixed weights wj for each time point tj. A different class of options is our so-called barrier options or discrete barrier options, where you say, for example, I have a down and out call. So I have a barrier level B, which is typically below the strike of the call option. And if along the way the stock price dips below that barrier, so if it crosses the barrier downwards, then the call option disappears. So this is the reason why it's called down and out. And if during the whole time the stock price stays above this barrier level, then I'm going to get my call option payoff. And I can represent this mathematically by saying I take the product of a bunch of indicator functions. So each time the stock price stays above the barrier, the indicator function is 1. But if the stock price at least once dips below the barrier, I get one indicator function that becomes 0, and then the whole product becomes 0. And that this basically nullifies the complete payoff structure. So I'm only getting my call payoff if at all the intermediate time points the stock price was always above the barrier level. And then another version, so this is kind of down and out, and another version is, let's say, up and in, or down and in type of options. For example, if we have an up and in put option, now we're going to put the barrier level above the strike level K. And then we're going to say the stock price first has to go through the barrier level. And then only then will you receive your put option payoff. So then your stock price has to move up first to reach the barrier level, and then kind of go down again to end up in the money. And again, you can represent this with a product of indicator functions. And there are many, many variants of these type of contracts. You can do combinations of in and out barriers. You can do double barriers where you say there is a barrier above and a barrier below. And you can have all kind of variants where you say it's a double out barrier, or you can have some things by saying I first have to get in the barrier, and then if I move too high again, I get clicked out again. So many combinations can be made, but the general observation is that all these type of payoffs, no matter how exotic with double barriers and whatnot, you basically have a recipe where you say, if I know at the end of the path, if I can look backwards what the path was that I followed, then I can basically determine the payoff, looking at whether I always stay below the barrier or above the barrier, etc. Final version, these are known as look-back options, where you say, I look back along the path and I look at the highest value that I observed along that path. And then you can either have a floating strike option, where you say, I compare the maximum with the final value. And you don't see a comma zero here, because by definition, if I include the final value in the calculation of my maximum, the maximum is larger than or equal to the final value. So this number here is like automatically like a call option. It is either a positive value or equal to 0. So this is a floating strike look-back option. You can also have a fixed strike look-back option, where you say, I first compute the maximum, and only if the maximum is above a certain level K, then I will be getting my payoff. And then obviously we have put option versions, where you typically look at the minimum observed along the path. These look-back options do exist in the real world. For example, in Dutch mortgages, you have something called, so if you go to your bank and ask for a mortgage, they typically give you a quote on a specific 5-year or 10-year fixed rate that you have to pay in your mortgage. But then with this quote of the bank, you can go back to your broker and then maybe negotiate a bit between your house. So typically Dutch banks make you an offer for this fixed rate in the mortgage, and that offer is valid for a period of either 3 months or 6 months. And then what some Dutch banks offer is by saying, if at the end of the 3 of the 6 month period, so by the date when you actually sign the contract of buying your house, you can then look back along all the interest rates that have been quoted by the bank during that period, and then you have the right to choose the lowest interest rate that you have seen during that period. So this is kind of a look back option, because you can look back at all the interest rates that the bank quoted between now and 3 months ago. And then you have the right to start your mortgage at this lowest interest rate that has been observed. And another variant, of course, that is not a look back, but just like a regular option, is where you say, we compare the offer interest rate, so from 3 months ago, with today's interest rate. And if today's interest rate is lower than the interest rate from 3 months ago, then you have the right to choose the lowest interest rate. So this is kind of a normal European option, but some Dutch banks offer a contract where you can really have this look back feature, where you can have the right to choose the lowest interest rate that has ever been observed during that offer period of the last 3 months. And this is then, and interest rate look-back option. And this is something we're going to talk about when we do interest rate modeling, interest rate option modeling. This is something we're going to cover next week. So how can we value these multi-look options? Well, the easiest way to value these multi-look options is to use Monte Carlo. And I said it a few times already, when you do Monte Carlo, you are literally generating a path of values. And if I have generated a path of values, then it's very easy for that one particular path to look back along this path and then basically evaluate your payoff function with the realizations of the stock price or whatever underlying value along this one path that you have generated. You need to discount this, or you need to divide by the numeraire. And then you repeat this 1,000 or 10,000 times and take the average of all these payoffs. So for these multi-look or look-back or maximum options, it is very quick and easy to implement in Monte Carlo. But the price you pay is that with Monte Carlo, you always have this 1 over square root of m, where capital M is the number of paths that you generate. This 1 over square root of m type of convergence. And we generate paths, then what we saw last week is that you can use the stochastic differential equation and you can use Euler discretization, but then you are generating a path kind of incrementally. You draw realizations of the Brownian motion or of the delta W's, and then with each delta W, you kind of push your stock price one time step forward at a time. And we can offer a slightly different perspective here is by saying, what is a path? Well, a path is a vector of random variables. And in many cases, when the underlying economy, like the Black-Scholes economy, or when the underlying economy is kind of easy enough, I can draw the vector of values, not sequentially, but basically simultaneously from a joint multivariate distribution. And at least what I can do is, instead of drawing the independent Brownian increments sequentially from a normal distribution, I can basically draw a vector of Brownian motion realizations from a multivariate normal distribution. And once I have this vector of Brownian motions, I can then compute the vector of stock price values from that W vector. And typically in matrix-oriented languages like MATLAB or Scilab, this allows you to do much faster Monte Carlo simulation because you are drawing directly vectors of realizations. And this avoids doing for loops in MATLAB, which are typically very expensive in terms of execution time. For example, if we consider the Brownian motion at 3 different time points, assuming that T1 is less than T2 is less than T3, then the vector of length 3 of WT1, WT2, WT3 is a trivariate normal distribution with mean 0, 0, 0, and with variance covariance matrix equal to the minimum of Ti and Tj. So you get this T1 sitting here. This is in the first row, in the first column and the first row, T1 is the smallest element. And then in the second row and column, T2 is the smallest element. And only in this bottom value, T3 is the smallest element. So we can draw, we can always draw for any type of model a vector of Brownian motion values directly from the multivariate normal distribution. And in many models, and in particular in Black-Scholes type of models, we know that the logarithm of the stock price at different points in time, that is also a vector with a joint multivariate normal distribution. And if you apply Ito's lemma, or you can basically compute in closed form what are the means and the covariances of these logarithms of the stock prices of the Brownian motion. And basically you can draw a whole path of stock prices or a whole path of log stock prices directly from a multivariate normal distribution. So Monte Carlo simulation is nice that you go along the path, but sometimes if you have like options with daily observations, or sometimes even with continuous observations, especially for these barrier type of options, and sometimes even for these Asian or look-back options, then Monte Carlo simulation can be a bit impractical, because then you need to do a lot of time steps to kind of approximate sufficiently accurately your daily or continuous observations. So we can sometimes do find closed form pricing formulas for these path dependent or for these multi-look options. And in particular, if you look at barrier or look-back options, we can reduce the dimension of the problem by saying, let's consider a cleverly chosen extra state variable that we want to keep track of. And typically for barrier and look-back options, you want to look at the maximum or the minimum along a path, and you view that maximum or minimum as a separate random variable, which is correlated with your final stock price. And again, in a Black and Scholes type of model, we know for Brownian motion, we know in closed form what the joint distribution is of the maximum of the Brownian motion and the final value of the Brownian motion along a path. And then if we have these Asian type of options, I can introduce a new random variable, capital A, which is this average of all those stock prices. And then I can view this average of all stock prices as a new random variable. And then if I know what the distribution or what the moments of that average are, I can approximately or exactly compute the price of these type of options. And what's the trick of using this extra state variable? Well, typically those payoffs are relatively simple. So then the option payoff is kind of a European type of option let's say, when I take this extra state variable into account. So I can take the final stock price and the maximum, so that I can use to do these look back or these barrier options. And if I take the final stock price and the average, I can typically price Asian options. However, you then, to compute this European option, you need to know the joint bivariate distribution of the final stock price and the maximum, or the final stock price and the average. And this is basically the basis for many closed form approximate pricing formulas for these multi-look or these look-back barrier type of options. Let's move to a different way of looking at options, and this is something known as static replication. So let's take another look at martingale pricing. So suppose I am viewing the payoff. This is like, for example, a finite difference grid, or in general, I have the stock price along this axis and I have time across this axis. And then suppose that I have a certain type of exotic option where I know the payoff along any of these red lines. And this is very similar to kind of knowing these boundary conditions for the implicit finite difference method. And typically for a European option, you are only using this final payoff at the end, and this top red line is basically pushed up to plus infinity. And if we have something like a barrier option, then we are typically explicitly given the value of the payoff at this upper or this lower bound. Here I've drawn this lower bound at 0, but this lower bound could have been at a higher value over here. Now, if the payoff, or if the value of the contract is given at a closed boundary like this, and it doesn't have to be these straight lines, it basically could have taken any shape. I think it has to be a convex shape. So if it's kind of a convex region, then if I know the value on the outside, then basically, because I'm doing martingale pricing and I'm taking expectations, then the expectation or the martingale property basically gives to me what the value of the contract will be along all the dotted values on the inside. And we know that taking expectations is a linear operator. So what's now a clever trick that I can do is, if I can replicate a payoff with a set of typically vanilla European call or put options, and I choose a portfolio of call and put options in a clever way such that I match the value of the contract that I want to price exactly on these three red lines, then by no arbitrage and by martingale pricing, it must be the case that on the whole inside region, the value of the exotic option and of my static replicating portfolio must be exactly the same. Because expectation is a linear operator, having a sum of instruments, if I take the expectation of the sum, that is the sum of the expectations, and anywhere on the inside we will also match the price because we are taking a sum of martingale values. And again, with every time I've said value here, it was of course discounted value or value divided by the value of the numeraire. Let's take a look at a very powerful example. If I push those upper and lower bounds away to plus infinity and minus infinity, or then if I have a payoff, this final red line here, it turns out that any function that I can have, as long as it is, I think, a twice differentiable function, I can basically replicate any payoff f of S capital T with a continuum of call and put options. And the trick that you do is you say, I choose a certain switch point f, and then between 0 and f, I am using all kind of put options, and I'm integrating over the strikes here. So I'm choosing a strike of 0, 0.1, 0.2, 0.3, 0.4, 0.5. So I'm integrating, or I'm adding all these different strikes together. And the weight that I'm using for each strike is the second derivative of the payoff function evaluated at that strike point. So if I take a bunch of put options with different strikes k, then the weight for each put option with strike k is given by the second derivative of the payoff. And I use all these put options up to the point f, and above the point f, I start switching to call options. And then again, I'm simply using the second derivative as my weight. And then because I'm using second derivative, it's like a second order differential equation. Looks like here I need two more boundary conditions. So at the point f, I am matching the value, and that is just a constant amount. F of capital F is a constant amount, basically invested in cash. And then I am taking a forward position, S capital T minus F, so I'm taking a linear position, and the weight of that linear position is the first derivative of F. And this is an identity, so I have this triple equality sign here, so this holds for any value of the stock price ST, because ST is kind of a free variable here. So if I match this function f with this portfolio of put options and call options, then if I take risk neutral expectations on the left side and on the right hand side, I basically get this identity for any payoff. And this formula has one additional degree of freedom. I can choose the switch point f conveniently as I want. And you can prove this identity by differentiating both sides of this identity twice with respect to the stock price, with respect to the stock price S capital T. So what are some examples? Suppose I want to replicate the stock price squared. I can do this by basically buying a portfolio of call options. And you see that each call option, I'm doing this piecewise linear approximation. And the second derivative of S squared is just 2. So I'm basically taking 2 times a portfolio of call options with all different strikes. And each call option gets a weight equal to 2. And that is basically applying this big formula over here, by setting capital F equal to 0. If I set capital F equal to 0, then all the put options disappear. And I know that S evaluated in the point 0 is equal to 0, and the derivative of S squared is 2 times S, and evaluated at S equal to 0 is also equal to 0. So also these first 2 terms disappear. And another type of contract, if I want to replicate the logarithm of the stock price, then I basically substitute this formula here. So that I take the logarithm in the forward point, then I take S minus F times the derivative of the logarithm, which is 1 over F evaluated in the point F, so that's this term here. And then the second derivative is 1 over F or 1 over X is X to the power minus 1. And if I take the derivative once more, I get minus 1 times X to the power minus 2. So that is this weight minus 1 divided by K squared. So that's exactly this term here for all the put options and this term here for all the call options. And these S squared and log S are contracts, and this replication method is really used for real contracts, because these are the basis for the so-called volatility index, the VIX. And these volatility index options basically track the variance of an underlying stock. And this variance can either be computed by taking the square, S squared, or you can take the logarithm of S, and if you then apply Ito's lemma, you also see that the variance of the stock price in the Black-Scholes world kinds of appears over here. So these payoffs and these replication formulas are really used in the real world. For example, in the definition of the payoff of a variance contract known as the volatility index, the VIX. Going back to the general case where we also have an upper and a lower boundary. So we know how to replicate any possible payoff at the end here. And then typically what you do is you don't want to use a continuum of options, but that's what I did with the dotted line here. I can use discrete points in time. And then I say I want to solve the payoff at each of these discrete points in time. And if I choose these discrete points in time sufficiently close together, then I am kind of approximating getting the payoff right on the continuum. So you are making a small discretization approximation, but what you gain with this is that you express your exotic contract in terms of a portfolio of vanilla options that are traded in the markets. Let's look at a specific example. How can we replicate a so-called up and in put option? So as I said, I choose a barrier level B that is typically above the strike K. So the strike K is somewhere here. So if the stock price goes first up and hits the barrier, then at the moment when I hit this barrier for the first time, I am getting this put option. And then if my stock price goes down again below the strike level, then I am getting a value for my put option. And if the stock price always stays in this region, even if it ends below K, because I have never hit this up and in barrier, the option expires worthless. And the way to replicate this is maybe a little bit surprising, is that I choose a set of time points Ti, and then at each time point Ti at the barrier level B, I know that at that point, if I would hit the barrier for the first time at that time point Ti, then I know I'm going to get a put option. And I can compute the value of that put option at the time when I'm getting it with the Black-Scholes formula. So I know what the market price is of the put option when I hit the barrier at the first time at time Ti. And then the question is, or what I want to solve is, I now want to use a set of call options with levels of strikes above here. So there are a bunch of call options that are sitting up here. And all these call options have the same maturity date, capital T, but different strikes Ki. And then the first strike that I want to use is kind of symmetrically located. So it is, you have B minus K going below, and then you can go to B plus B minus K going above. And then I need to do some logarithms, but you get a value B squared over K. And the reason for kind of mirroring or reflecting this payoff, this put payoff below the barrier to a call payoff above the barrier, this is kind of explained in Joshi's book as something called the put-call symmetry. And then if I use these call options with the same maturity date, but with these different strikes, then if I have 1, 2, 3, 4, 5 time points TI, I can kind of use 5 call options with 5 different strikes. And then I can basically say, I want this basket of all 5 call options to match at T5, T4, T3, T2, T1, and then I get a system of 5 equations with 5 unknowns that I can solve. So I've done this example here. Then I say I want to replicate a 1 year up and in put option, and the current strike price or the current stock price is 100. The barrier level is at 110 and the strike price is at 90. And then I want to match the value of the put option at time t at the barrier at time 0.9, 0.8, 0.7, all the way until time 0.1. So then I have 9 time points where I want to match the payoff. And then I can choose 1, 2, 3, 4, 5, 6, 7, 8, 9 call options with strikes at 134, 139, 144, and I've arbitrarily chosen a step size of 5 here, so you can play with that a little bit. And then you see that the largest call option is a position of 0.688 in this first call option with this strike here. And that would be a straight line going up. But then because of this put call reflection, it turns out that the reflected put option, because of this logarithm transformations, is a little bit bending down. So therefore, I am over hedging by just doing that simple call option with a position of 0.688. So for the higher strikes, I need to sell off. I need to go short a little bit to replicate this kind of downward bending shape. So you see a large position of a positive position of 0.688, and I'm taking the small correction position of minus 0.05, minus 0.02, da, 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 da. And then you see that the blue line is kind of the piecewise linear call payoff of the sum of all these call options is this blue line. And then I know for this case, because I can have this reflected put option, as Joshi explains in chapter 10.6, the orange line is kind of the let's say, the true reflected put option. And we see that this replicating portfolio very closely follows this, this reflected call option as a sum of call options. Okay, let's move to the third part of the lecture. And here we are going to talk about so-called American style options. So what we've done so far is we have basically taken a look at European style options, where we say at the final date, capital T, you determine what the payoff is. And maybe with these look back options, you do kind of look back, or with the barrier option, but basically say I wait until the final date, capital T, and then I determine what my payoff is. Now, and these are known as kind of European style options, or maybe exotic European style options, because European style basically means you wait until the expiry date and then you get your payoff. And an important other class of options are known as American style options. And with an American style option, you have a so-called early exercise feature. And this means that you, as the holder of the option, you can choose when you want to early exercise, or maybe you don't want to early exercise, and then you just wait until the end and you get your payoff at the end. Now, choosing when to kind of stop using the option and early exercise is mathematically known as a class of stochastic optimal control problems known as optimal stopping problems. And just from the simple observation that if you don't stop early, this may be suboptimal, but if you don't stop early, you're always going to get your European style of payoff. And if you're a little bit clever, then if you optimally stop early, you can increase the value for your option. So an American option must be the case that the value of an American option is larger than or equal to the value of a European option, because an American option where you simply always wait until the end, is exactly the same as a European option. And then if you are a little bit more clever, then if you optimally early exercise, you will only increase the value of the option. So what are examples of American style options? These are widely used in the real world. Is that if we look at stock options on individual stocks, like individual companies like Philips or ING or whatever. So equity options on individual stocks traded on the exchange are always American style options, except for options on the index, because options on the index are European style. If we take a look at Dutch mortgages, there you have something called in Dutch rentebedenktijd. So this is kind of interest rate revision time, where you say, suppose you have a 30-year mortgage with a 5-year fixed rate. So for the first 5 years, you are paying a fixed interest rate. Then during the last year of that 5-year period, you have the right to say, I now want to lock in a new fixed interest rate for the next period. And there are two choices that you can make. You can do this timing choice that makes this option, let's say, American style or limited American style. And furthermore, you can say if you now have a 5-year fixed rate, you are free or you have the right to choose a different type of fixed rate for your next period, as long as the fixed rate does not exceed the total maturity of 5 years, of 30 years. So in this example, during the last year, so from TS4 to TS5, you have the right to say, I want to choose a new fixed rate. And I can also choose the length of the fixed rate anywhere between a floating interest rate up to 25 years. And that is kind of an American style option because you have the right to time this decision during the last year of the fixed rate period. And then if we have life insurance products, typically with guarantees, then many life insurance products allow you to invest in an underlying investment portfolio. And then you sometimes have the right to say, I have the right to kind of change the composition of my investment portfolio during the life of this insurance product, but the guarantee level basically stays the same. So this is an American-ish type of option because you have the freedom to do something during the life of the product. So this is American style, but it is more complicated, like with the mortgage a little bit, because when you exercise, you don't lose the option. You can basically say, I change the composition of my investment portfolio. So how do we solve this optimal early exercise or these optimal stopping type of problems? And for those of you who maybe did some OR courses, we know that we can solve these optimal stopping type of problems via so-called backward induction. And then we use Bellman's principle of optimality. And basically Bellman's principle says is, if I have already solved what the optimal solution is from this point going forward in time, if I then take one more step back, I only have to add, let's say, glue onto the optimal path that I already have towards the end. I only need to do one more time step and only make the optimal decision during my current time step. And then with backward induction, you are basically rolling backwards in time. And then for each time slice, you are kind of saying, I'm adding I am extending my optimal path with one more time step. So how does this work for American style options? Is to say, suppose that we have a payoff function small g at time small t given some underlying state variables, maybe the stock price or the Brownian motion, x at time small t. And if I exercise my option, I am getting this payoff g small t given the state of the world x of small t. And now I want to maximize this value function over all random stopping times tau. So in mathematical notation, I want to maximize over my stopping times tau the Q expectation of the discounted payoff of getting my payoff at time tau divided by the value of the numeraire at time tau. And then a feasible solution is to say, and obviously, and it can be quite suboptimal, but a feasible solution is to say, I choose, instead of using a random stopping time, I always wait until the end. So I set tau identically equal to capital T, and then I'm basically getting my European option payoff back. So this is a feasible solution. And if I do a little bit more optimal on top of that, I can only increase the value of this option. And how can we find this optimal random stopping time process tau star? The way to do that is to use backward induction. So suppose we have already solved our optimal stopping for times tau later than my current time t. Then what is my optimal choice at current time t? Is actually quite easy because I compute two things. I first say, suppose that I would not exercise today, then I get basically the value of the option in the next period, and I use this martingale pricing. And this green term is known as the continuation value. So this is the value of not exercising today, but wait until next period. And then for this next step, it behaves like a not exercised option. So it behaves like a European option, and I basically can use my martingale. But this is a conditional expectation, conditional on every state of the world x of small t at time small t. And then once I have computed my continuation value, then you're going to say, but now I'm going to check. I know what the value is of not early exercising. And then basically for each state of the world x at time small t, I'm going to compare the continuation value with the early exercise value. And then obviously, I take the maximum of those two values. And typically what you get is that you get a so-called exercise boundary. There is a kind of a unique point, which I call x tilde at time small t, given the underlying Brownian motion or given the underlying state of the world. And then above x tilde or below x tilde, you are continuing or exercising, etc. So with backward induction, it's relatively easy to solve this optimal stopping problem because you make two separate computations. You first compute the continuation value. What's the value of not exercising and waiting until the next period? And I compare that to the value of immediate exercise. And obviously, I maximize my value by taking the best of two options for each possible state of the world. And once I've solved it for time slice t, I then move back one more time slice and basically resolve this optimization problem. So American style options are very easy to value with tree or partial differential equation type of solvers, because in a tree, you are already doing this backward induction in time. If you do a European option with a tree, you start at the final date to look at the payoff, and then you basically step forward or you step backward until time t is equal to 0. And in a binomial or trinomial tree, you are literally computing this discounted payoff. It's the up probability times the up value plus the middle probability times the middle value plus the down probability times the down value, and then you multiply this expectation with e to the power minus r delta t, or 1 over 1 plus r delta t. And this conditional expectation is literally this green term from the previous slide. It is this conditional expectation, conditional on where you are currently in the grid. If you want to include early exercise in your tree or partial differential equation or finite difference calculation, it's really easy, because you first compute the green term like you would do in a European option. You just compute the continuation value, and you only need to do one extra thing, is by saying I have now evaluated my conditional expectation or my continuation value for all my states of the world j in the time slice I. And then basically for every state of the world j at time slice I, I'm going to compare this continuation value with my early exercise value, and I take the best of the two. And that is then my updated value for Fij. So this, quite literally, we implement this backward induction algorithm quite literally in our binomial, trinomial tree, implicit, explicit finite difference solver. So that's quite easy. But as we have seen earlier, tree and PDE solvers only kind of work for low dimensional type of problems. So can we do American style options with Monte Carlo? The problem is, or initially, it seems that Monte Carlo is like doing it's a forward type of algorithm. I start at time 0, and then I'm generating one single path going forward in time. And then along this one path, I can kind of do compute my payoff at the end. So because Monte Carlo is kind of a forward type of algorithm, whereas for optimal stopping, you need a backward induction type of algorithm, it was quite long believed. And when I was at university in the 1980s, I was being taught during the course Mathematical Finance that it was not possible to value American style options with Monte Carlo simulation. So this was quite long believed that this was not possible. But then at the end of the 1990s, there was kind of a series of papers that actually showed that it is possible to do so. And the most, let's say, famous of those papers is the Longstaff and Schwartz paper from 2001. Why is it possible to kind of combine this forward generation of Monte Carlo with this backward looking? For that, we need a slightly different perspective or another look at doing conditional expectation. And this is also kind of the mental barrier that kept people from actually understanding that it is possible to do Monte Carlo, American options with Monte Carlo. So if we take a conditional expectation, so if we take a function f times small t at state of the world x small t, which is defined as the conditional expectation of some payoff at a later date, f capital T, then we can view the conditional expectation as the following solution to a quadratic minimization problem. I want to find that function f, which is measurable at this earlier time point, so that only depends on information at the earlier time point small t, that is as close as possible to the later payoff at time capital T. And obviously, because I'm missing information and I'm earlier in time, there is no way I can get a perfect match. But it is a well-defined problem to say I want to minimize the variance. So I take f at time big T minus f at time small t squared. And I want to minimize this quadratic difference. And I'm taking the expectation of this quadratic difference. And so a conditional expectation is the solution of this minimum variance problem. So one way to look at conditional expectation is to say, what is the minimum variance approximation of the payoff at a later date at time capital T unto my, let's say, situation where I have much less information because I don't know what's going to happen in the future. And another way of saying I want to minimize this variance is like I'm saying I'm doing a projection of all functions that are, let's say, measurable with respect to this later information onto the space of functions that are only measurable with respect to this earlier information and to this less information at an earlier time small t. And doing a minimum variance projection is exactly the same as doing a least squares regression. And this is kind of the magical insight that we need, that we can use in a Monte Carlo setting, because in a Monte Carlo setting, we have much more information than this one path. I can basically say I have 1,000 paths generated, and I can basically look cross-sectionally at a certain time slice across the 1,000 or 10,000 paths that I have generated. And I can do a least squares regression cross-sectionally across all the paths that I have at a certain time slice t. And this is kind of the magical trick for an algorithm known as least squares Monte Carlo. So how do you apply this in practice? Is by saying, how can I approximate this function space of functions that are measurable with respect to this information at time small t? Is by saying, I can span this function space, or I can approximate this function space by using a set of basis functions. And these basis functions are only a function of the information or of the random variable at time small t only. And it sounds maybe a bit, let's say it's the same idea as just using a vector space Rn. We can view a space of functions also as a vector space, and it does have a basis. So what kind of bases do we have for these function spaces? Well, polynomials is a very well-known example. And again, let's say any kind of nice function can be approximated with Taylor approximation. Well, this Taylor approximation is kind of using these polynomials as basis functions to approximate a function space. And another example we have already seen is we can use these sine and cosine functions. And then we have these Fourier bases. So sine and cosine functions with different periods. We typically then choose integers and maybe multiples of pi. So we choose the sine of pi times x and 2 pi times x and 3 pi x and 4 pi x. That collection of sine functions with increasing frequencies is a basis for a function space. And this is a very active field because neural networks is basically also using these basis functions of function spaces. So how do we do this in practice? Is that we say, I have a collection of paths, and then for each path, small m, I have at time small t, I know what the current value of the stochastic process is in path number m at time small t. And I also know what the payoff along each path is going to be at the future date capital T. So because I have each path, I can basically look into the future. I can peek into the future along this one path. And then I say, I know at time small t, what the payoff is going to be at a later date capital T, or maybe a later date tau when I'm using this optimal stopping. And now we have capital M independent paths, where I'm basically regressing the payoff later in the path onto the current value with these basis functions hk at time small t. And here you see this kind of projection happening. I am regressing my payoff at a later date onto these basis functions, which only use the current state of the world xm at time small t. And this is a linear combination. So this is kind of a classical regression, and I can estimate my coefficients beta hat of k for how much loading do I have for each basis function hk, how much weight beta k do I give to each basis function. And then taking a conditional expectation, I basically remove my epsilons, and then the conditional expectation that I get is then evaluating the basis functions at time small t using my regression weights beta hat of k, and that gives me my conditional expectation. So the conditional expectation is then literally the least squares or the minimum variance approximation of the payoff at a later stage in the future. And of course, I can't reach the future, but with the Monte Carlo, I can kind of I can take a sneak preview of what's going to happen into the future, but then I'm going to say I'm not allowed to use that future information. So I have to project this future payoff back onto the basis functions that only use the information and the value of each path at time small t. So the least squares regression leads to these estimates beta k. And because I have m independent paths and the epsilon terms are independent with mean 0, you can prove mathematically that these least squares estimates lead to unbiased estimates if, of course, the number of paths is approaching infinity. So how do we compute an American option with a least squares Monte Carlo? Is I start by generating capital M paths of let's say my stock price going from time 0 to time capital T. And M is typically a large number like a 10,000 or 100,000. And then I say I'm going to start at the end. I'm going to start at capital T, and I'm basically going to, for each path, I'm going to use the European payoff G evaluated at time capital T in path number M evaluated at time capital T. And this is basically saying that for each path, I'm going to set the early exercise date at the final date for all the paths capital M. So I'm basically loading my Monte Carlo simulation with the final payoff at the final date for each path M. And then I'm going to start a backward induction loop by taking discrete time steps I delta t. And then I'm going to do a regression by saying for each path, I know when I'm going to exercise. So I have my stopping time tau m in each path number M. And I know the payoff x tau comma m that I'm going to get in path number n m at my stopping time tau. And I'm going to project, all these stopping times are lying at later dates beyond I delta t. And I'm going to regress those future payoffs at those later dates onto basis functions at the current time slice I delta t. And after I did this regression, I have an estimate for my continuation value at the time slice I delta t by basically taking those beta hat values from my regression for the time slice I delta t, and then multiplied or times each basis function, a constant x, x squared, x to the third, etc., etc. So now I have estimated my continuation values with the conditional expectation using this regression. And now I'm going to check for each path, is the continuation value that I have larger or smaller than the value of early exercise today at time I delta t? And for all the paths where the early exercise now at time slice I delta t is better, I'm going to update my stopping time from the old value of tau m to the new current value I delta t. And of course, I'm going to update the payoff that I'm going to get at this path, at this new updated exercise. And then I have updated my early exercise values for each time slice I delta t, and then I continue my loop by going to I minus 1 delta t, and then I'm going to start again until I reach time 0, and at time 0 I have then a Monte Carlo estimate of my American style option using this so-called least squares Monte Carlo algorithm. There is a slight problem with least squares Monte Carlo is that you are using these in-sample regressions, and you are basically using a little bit of information from the future. So you are overestimating the effectiveness of your early exercise because you are a little bit looking into the future, because you keep reusing the same set of sample paths to do all these regressions. This is not a big problem in reality, but it can sometimes be a little bit of a problem. And if you want to be absolutely sure that you haven't been looking too much into the future, the way that you implement least squares Monte Carlo is you do kind of a two-step approach. So in the first approach, you generate M paths, and then you use this regression algorithm, but then you keep track of basically what the early exercise region is that you estimate for all these sample paths. So you kind of keep track of at which time point or at which state of the world do you switch from not exercising to exercising. So you are basically estimating this x hat at time I delta t for all these time slices I delta t. And then to avoid that you pollute your estimate with this looking into the future, you basically keep this exercise boundary, but then you're going to re-simulate a new set of paths. And then you say, using this new set of paths, combined with my old exercise boundary from the previous round, and then simply evaluate the payoff on this exercise boundary. So I'm not doing any regressions in this second round. I am basically redoing my simulation and evaluate the payoff based on my exercise boundary from the previous round. And then this kind of two-step solution is guaranteed to give you a lower bound, because you've used this regressions. You are always getting a suboptimal exercise boundary, so you are guaranteed to underestimate the true value of the American option, and typically you are very close. But sometimes you want to be absolutely sure about, let's say, how large the error is that you are making, because you cannot compute these standard errors anymore. So there are standard errors involved, but you have an additional source of errors. Is that how accurately did I approximate the true early exercise boundary? And it's a little bit more difficult, but Yoshi in chapter 12 kind of explains that you can also use a method to obtain an upper bound with Monte Carlo simulation. But I leave that for you to read. What most people do is kind of believe that the least squares Monte Carlo is good enough, and they basically use the least squares Monte Carlo by saying, and then I accept that I may have a suboptimal exercise boundary, but I kind of know that I am approximating the true value from below if I do this two-step type of simulation. That's it for this week, and I'm going to stop the recording.